So the first type of absorption spectroscopy that we will be talking about is infrared spectroscopy, or IR spectroscopy. The range is from 780 nanometers to 1 millimeter. So in IR spectroscopy, it exploits the fact that molecules absorb frequencies that are characteristics of their structure. So these absorptions occur at what's called resonant frequency. So these are the frequencies where the radiation, the absorbed radiation, matches the vibrational frequency. So a requirement for IR activity is for a vibrational mode to have a change in dipole moment. So a permanent dipole is not always necessary. This technique is commonly used for analyzing samples with covalent bonds. So here are just some examples of vibration modes. You have symmetric and anti-symmetric stretching, scissoring and rocking, and wagging and twisting. So if the vibration modes, upon interaction with the light, if the dipole moment is changed, then it is IR active. It will show on the IR spectra. So here's just an example of an IR spectra of formaldehyde. Trained chemists will be able to interpret these peaks and assign each peaks with the type of the bond and the type of the vibrational mode. So the IR spectrometer that is commonly used these days is what's called a Fourier transform infrared spectrometer, or FTIR spectrometer. So here's a simple schematic for FTIR. So remember, on the general schematic, you let light pass through the sample and then it gets detected. On the FTIR instrument, you use what's called an interferometer. So what it is, you have an IR source and then you split it into two at a 90-degree angle, and then when they recombine, if the phase of the light are the same, what happens is constructive interference, which creates a more amplified light. So in other words, in this setup, your detection will be more sensitive. So what you get is what's called a time domain interferogram, and a chemist doesn't really know how to read that, so yeah. It has to be converted first using a mathematical transform called Fourier transform. That's why it's called Fourier transform. And what we can read is the frequency domain spectra. That's what we can use for our purposes.
Yep, and just like one talking point to inspire our students, Dr. Dindi.
Mm-hmm.
So Dindi talks about an IR. She showed an IR spectrum. So one very important thing that our students should really have like a fairly deep appreciation of would be Lewis structures, and then the concept of polarity, band polarity, because these all have relationships with the types of the signals that you would actually see. So for example, typically polar bonds, they would have some fairly strong responses to IR. So that has something to do with the polarity and the strength of those bonds. So it's very important that you're very familiar with Lewis structures, with bond polarity, and also different types of functional groups that would actually respond to photons.
100% agree. So here's just more example of spectra, IR spectra, sucrose and glycine. As you can see, I got these from NIST chemistry webbook. So there's actually thousands of spectra available online, and you can just download them and then use these as like your reference spectra, especially if you're determining the structure of your compound or your of your compound of interest or your analyte. So just like what Dr. Brunquin said, based on the bond polarity and Lewis structure, the bands of these bonds, type of bonds, will show at different frequency numbers. So here's just a list of main IR spectroscopy bands. You will see that on the left side you have the more electronegative or more polar bonds compared to the ones on the right side, and so on and so forth. So IR spectroscopy is normally used for qualitative applications. You can use it to identify functional groups and structural elucidation, identification of substances, because these spectra are unique to that particular substance. When you're studying the progress of reaction, and when you're detecting impurities.